Hello, and welcome to episode 23 of Chemistry in 15 Minutes or Less. My name is Audra, and this review lesson is on chapters 10 and 11, part 1, Kinetic Molecular Theory and States of Matter. So, since it's in the title, let's quickly define kinetic molecular theory, because we'll start coming back to this. Kinetic molecular theory is based on the idea that all particles of matter are always in motion. This is how you explain the properties of liquids, solids, and gases, because they can be explained in terms of the energy in particles and the forces between them. Some of the attractive forces that are included in this are electrostatic attraction, which is the strongest and is also ionic attraction, dipole-dipole interactions, and, as the weakest, London dispersion forces. So, since we've covered what kinetic molecular theory is, let's get into the different states of matter, their properties, and how we can tie this back to the fact that particles are always in motion. Let's start off with something simple. Solids. Now, in a solid, particles are packed very, very closely together in this state. The intramolecular forces are the very strongest here of all the other states of matter. You might be familiar with what a nice ordered solid look like, where these are just different atoms or different molecules. Just fit nicely together, nicely packed. It's important to note that they are limited to only vibrational movement around fixed points. Solids still move. The particles never actually stop moving, except at the theoretical absolute zero. But they don't move out of this state. They just stay as a solid. Now this is the most ordered of the states, as remember we talked about crystalline structures in solids, or ionic compounds. But some properties that you need to know for solids is they have definitive shape and definitive volume. They also have a definite melting point, pretty high density, a relative incompressibility, and a low rate of diffusion. Like we talked about, they are orderly and geometric as far as orderly goes, and have repeating patterns, and some, like we talked about, have crystalline structures. Solids are pretty easy. It's kind of strange to think about a solid moving, but nothing's ever completely still. So let's move on to the liquid state. Now, particles are still packed closely together, but they can still slide past each other. So if you want to think about a liquid, they're still sort of packed together, but they're not in the same sort of orderly geometric structure that we saw with the solid. Now, intramolecular forces are less strong than solids, but are still better than those of gases. They have less limited movement, obviously, and no fixed points. They're still slightly orderly, they're not completely random. But as far as property goes, they have definitive volume, but not definitive shape, because this is what you'll remember, liquids take the shape of their container. They also have fluidity, which means they can flow, relative incompressibility, same as solids, good diffusion and a high density, and some other important properties of liquids are surface tension, capillary action, as well as evaporation, and we'll talk about the difference between evaporation and boiling. Now, surface tension is what you observe when you did that penny lab that I know we've all done, where you have the water that sticks in a dome. This is still showing that there are intramolecular forces that are holding the water, in this case, together on top of the penny. Basically, this is still with the kinetic molecular theory because there are intramolecular forces holding the liquid together. They are still moving because they can flow, like we talked about fluidity, but in this case, they are still wanting to stick together. Now, capillary action is basically what happens when, let's say you have spill of water and you want to mop it up. So you get a paper towel. It's going to be gray because I can't draw white on white. Now you notice that the paper towel starts out as dry, but gradually, the further along you get, the water will be sucked further and further up the paper towel, drenching it as it goes along. That is what capillary action is. It's basically that as the water starts to get absorbed, it's going to pull the rest of the water with it. And the difference between evaporation and boiling. Evaporation is when you have that puddle of water sitting on your desk, and the molecules at the top change state. That is when the top ones become a gas, and they evaporate off of the rest of the molecule. This is what happens when you sweat, when the molecules on the outside evaporate away from your skin, which is why it feels cooler, because it takes energy to transform a liquid to a gas. Boiling, however, is similar to evaporation, except for boiling is not specified to just the top. It's like when you have a pot of water, and you'll notice that bubbles rise, because it's starting from the inside of the liquid or sometimes the bottom, depending on how high you have the heat. Now, we don't actually get to talk about gases. We have to talk about ideal gas assumptions first. Because in order to follow kinetic molecular theory, we have 5 main assumptions about what an ideal gas would do. The 5 assumptions are that gases consist of large numbers of small particles that are very, very far apart. So that means that gases are mostly empty space. Or as empty as you can be. The second one is that all collisions are elastic collisions. Which basically means that when 2 gas particles smash into each other, no energy is lost. That would be if you were playing a game of pool and you know how when the balls hit each other, they slowly lose their kinetic energy because of friction and other things. Ideally, when gases knock into each other, you wouldn't have any loss at all. They keep moving at the same speed after knocking into each other. Now, 3, we have that particles are in rapid, random, and continuous movement. And for 4, we have that there are no forces of attraction. And 5, that temperature depends on average kinetic energy. Now we do have an equation with this that I don't know if we have to memorize or not. It's been unclear if we need it, but here it is. Kinetic energy equals half mass times volume squared. Now, as you know, these do not hold true with gases under most conditions. They don't have perfectly elastic collisions. There are still attractive forces between them. But they do behave like this under high pressure and low temperatures. Or at least they behave close to these conditions. Now we can use these 5 assumptions to base a couple of gas properties that we observe in still regular gases and in the perfect ideal gas. These include expansion, fluidity, low density, and a high rate of diffusion, which are all pretty self-explanatory. And with that, we should actually conclude episode 23 of Chemistry in 15 minutes or less. Feel free to leave questions or suggestions in the comments below, and be sure to follow the in-video links, check out the playlist, or head over to my channel for more videos on chemistry review. As always, I hope this is helpful, and have a great day.